right, gentlemen. Give me just a moment while I finish taking attendance as I let your brothers in. I should be streaming, so we are live streaming. If you have questions, it is a good idea to just make use of the chat, right? So just type it in the chat for right now. That's probably the best, just to try to minimize all my distractions so I can kind of like focus. But feel free to unmute yourself if I'm not responding, and just use the chat as well if you have questions about things. Okay. So I'll kind of keep this off to the side. Let me see. I think you guys can hear me. I usually like to do like a call and response, but you know, we kind of be having like packed houses. Let me see if I can think of any announcements. So we're wrapping up. This is going to be the conclusion of week 2, right? So the main point, honestly, the main thing is your assignments in Pearson. You want to just be sure that you have access to that. You access it through Blackboard. Uh, can you guys hear me okay? Feel free to type in the chat. Okay, cool. Okay. Yeah. Yeah, you just access the assignments through Blackboard. It's folder number 4 once you get into our content section. Right now, I only have the homework assignments available. In the coming days, I want to go ahead and make all of your quizzes for the semester available. And really, all I really intend to do is just keep moving forward with the lectures. I did make some updates to Blackboard, so just kind of go through it, peruse through it. I uploaded some handouts. I think I loaded a section for tutor information. So on Blackboard, there's a handout in there for tutoring. Also, I made a Dropbox, so like if you want to load the last page of the syllabus, you can load it there. Also, I loaded an updated syllabus, so if you wanted an updated syllabus, that's available in Blackboard. Our Blackboard, that's going to be our point of contact for everything. So if you have questions about how to find anything or where it is, it's in one of those folders. It's like 8 folders now in Blackboard, right? So you want to start there and like kind of try to follow the prompts to get what you're looking for. Okay, so not too bad on the timing. I got started a little bit later than I would have liked, but you know, we're here, we're present, we're accounted for. We are missing some of your brothers. Also, again, if you have I don't know if you guys did the group me or not. I think this class did, but it is a good idea to have the contact of at least like 2 or 3 of your classmates in all your classes. So you see, like, okay, and again, we are doing asynchronous, so you're not required to stay. Once you've got into the Zoom, you've got your attendance credit for the day. If it's overwhelming, which I totally get, you don't have to stay, but you are responsible for the material. These sessions are being live streamed on my YouTube channel. So you can always kind of go back and sit down with someone and watch it at your leisure. And the main thing is, as long as you're submitting your assignments via Pearson, that's going to be the bulk of your grade. Keep in mind with our assignments on Pearson, we get unlimited attempts, and you can submit any assignment late, like past the due date, with only a 10% late penalty. So that means that honestly, if you want an A minus on any assignment all the way up until the very end, shy of like a couple of exams, you can get an A minus on anything all the way up until the end. Okay, so it's the path is laid before you. You just have to make a plan, and you know it works if it works. It works if you work it, right? You know, hard work works, right? That's kind of what I was trying to get at. And then one other thing is like, I don't know if you know what the word system stands for, but system stands for saving yourself stress, time, energy, and money, right? So, you know, we all have a decision to make. We all have a path to walk. You know, you just have to do your best. One other thing, I'm gonna get off the little preacher box. Do your best, forget the rest, don't stress, and be blessed, right? So what that means is that like just do the best that you can, and like nobody can ever fault you for doing your best, and just know that no matter what happens, there's always a way to get something done. If if you're like working with someone, whether it's your professor or a colleague or a clerk or anybody like that, if you're working with someone and they're not saying what you need to hear, then that just means you're talking to the wrong person, right? So just know that one, ultimately everything is going to be fine no matter what happens. Two, if whoever you're talking to isn't saying what you need to say, hear, that just means you're not talking to the right person. Go ahead. Somebody has a question? Okay. So what I like to do today, I just kind of want to keep moving forward with the lectures, right? So we've done section 1.1 and 1.2. Um, and basically what I've been doing, I think I'm stalling to try to give students a chance to get in. I just want to view the waiting room. How do I view it? Oh, here it is. It's over here on the side. I think he was in here and got booted. Yeah. Okay. Cool. Okay. Um, I kind of lost my train of thought, so it's totally okay. Maybe I'll put this here. No. Can I shrink this down? Anyway, let's kind of get into it, right? I can't think of anything else that's pertinent. So, but Blackboard is going to be our main point of contact for everything. And everything is there. You just have to take your time. You have to make a plan, work the plan, and just get the stuff done. Like that's it. Um, Hopefully not being overly simple. All right. So today I want to move forward with the next section. This is the section I intend for you to use next week, but we can just go ahead and talk about it now. It's recorded, so and again, this is asynchronous. Once you get into my Zoom class, you've gotten your attendance credit. Let me pause for a moment. Did you guys have any questions about anything, like the homework or how to find things? Again, I created an updated syllabus. I loaded it in Blackboard. If you want to use that last page to sign, and I think I created a Dropbox link. It should work in Blackboard. It's going to be folder number 8, where you can load files that you need me to see. Right. The last page of the syllabus. Let's see. Oh, he was here as well. Okay. Last page of the syllabus. It's just for records, honestly. I used to use it for some other things, but it's mostly for record keeping. Let me check the chat. I think if I go like this, can I do it here? Come on. Let's see if I go like this. There it is. Okay. Yeah, they probably are using the wrong Zoom link, so they need to be redirected. They need to go use the links that are in Blackboard. It's in Blackboard. Just tell them to enter the Blackboard. I'll give them time though, because I know we're still kind of getting acclimated, and I did change some things. Um, but yeah, just tell them that they need to just or you guys can invite them, but those links in Blackboard should be updated. Um, yeah, and it is different from the initial link that I did. So this is an updated link. So just redirect them to Blackboard. I'll give them time to get in. It'll be okay. They just need to get here. Okay. So we're moving forward with section. I'm going to go ahead. I'm going to mute the audio right now just so I can focus, and just either raise your hand or use the chat. Let me see. Use the chat if you have concerns. I'm gonna let them in, but I'm going to mute the audio so I can focus. Okay. So section 1.3 is concerning functions. Some objectives here. We want to use functional notation and find function values. We like to find the domain of a function. We want to identify the graph of a function. We want to get information about a function from its graph, and we want to solve applied problems using functions. So let's look at some definitions. A special relationship such as y equals 10x, in which to each element x in one set there corresponds a unique element y in another set, is called a function. Y is sometimes referred to as the dependent variable and x as the independent variable, right? Let's see. Yeah, I can't think of anything there, so I'm going to let it be. So a function from a set x to a set y is a relation in which each element of x corresponds to one and only one element of y. Let me see. We got some activity. Let me see the activity. Yes, Mr. Overton, you are in the correct location. You did get attendance credit for the day. If you have concerns about the past, just kind of catch me towards the end of class, and we'll make sure that you're doing what you need to do. But yeah, I see you, and you're in the right place. You're on my roster. You got attendance credit, so I think we're good to go. Yeah, I muted the audio just so I can focus. Outside of class, I think they're using the wrong link, so they just invite them or redirect them back to Blackboard, right? Because I did update the link, because the one before was my personal one and that had the limitation. This one does not have is not limited, so I'll give them time to get in. Um, you know, because I did have to do some updates. I finally got access that I needed, so they just have to keep trying. And if you guys can get in, that means they can get in too. All right. Okay, let's kind of keep it moving. But yeah, just kind of help them out, redirect them, point them where they need to go. They're probably in the wrong link though, the wrong set. The set X is the domain of the function, and the set of those elements of Y that correspond or assign to the element X is the range, right? So again, a function from a set X to a set Y is where each element X corresponds to exactly one element of Y. Every X corresponds to exactly one Y. That's what we consider to be a function. The set of inputs, which is the set X, which is the set of inputs, we call that our domain. And then the set of outputs, which is our Y element, we call that the range, right? So for each X in the domain of F, that corresponds a unique Y in its range, okay? The number Y is denoted by F of X is read as F of X, right? I don't know, I think you can see, I'm not sure if you can see my cursor or not, but this F of X, let me see. Yes, it's no worries. I see you. You got your attendance credit. The number, let me see, this F of X is read as F of X or F at X. One common error is when people see this F parentheses X, they think it's multiplication. That's not multiplication, right? We call F of X the value of F at the number X, and we say that F assigns the value F of X at the value to X. Kind of a mouthful. This will become clear as we kind of work several examples. Let me make sure this student, give him his credit, and boom, he's in there. So functions can be defined by ordered pairs, tables, and graphs, and equations, okay? So let's look at this example. We're asked to determine whether each relation defines a function. So whenever you hear me pause, I'm like taking attendance and letting people in. Because I do realize we're still getting acclimated, things are getting updated. So I'm a little bit lax the first week or so. Determine whether each relation defines a function. For part A, we have R equals this set of ordered pairs, and in part B, we have this set of ordered pairs. So one property of functions is that each X corresponds to exactly one Y. Let me check the chat real quick. Yeah, it's cool beans. I have 2 on Blackboard. You sure you, I mean, that could be the case. How did you get in, Mr. Briggs? How did you get in? Like what link did you use? I just probably have to go back and update all of those. It's probably did you use the QR code? Here, let me unmute the audio. Don't worry about the 15 minutes. Mr. Briggs, how did you get in today? I'm curious, because if I have 2 on Blackboard, I gotta. Which one did you use initially? I'm trying to find the wrong one. The QR code? Okay. Yeah, I'll update that then. Okay. Because I thought I did update it, but I guess I hadn't. So I'll just redo that. Thanks for that. Okay. I'm going to mute the audio. Just kind of keep helping your brothers. They'll get in here sooner or later. It'll be okay. Hopefully. It will be okay. Not hopefully. It definitely will be okay. But I'm going to mute the audio right now and so I can focus. So we're going to go back. Again, it says determine whether each relation defines a function. So if we look at part A, now again, one property of functions is that each X corresponds to exactly one Y. If you have one X that corresponds to 2 different Y's, then we say that's not a function, right? In other words, in this form where we have this list of ordered pairs, if we have repeating X's, then it's generally not a function, right? So if we look at part A, let me see, let me go like this. If we look at part A, do we have any repeating X's, right? We got a -1 here and a -1. So we have one X that corresponds to 2 different Y's. So that one should not be a function. All right, so we would say that this is not a function because basically we have repeating X's. Let's look at part B. Do we have any repeating X's? Uh-oh. Do we have any repeating X's? No. Just like in life, repeating X's might not be a good idea. I mean, it's not always bad, but, 9 times out of 10, repeating X's usually leads to turmoil and suffering. Usually. Not always. There's always, room. You're right. What you're going to discover is a lot of the things I say in this course actually mirrors or parallels your regular waking life. Uh-oh, didn't want to do that. Let me check the chat. I do that all. It's like a whole bunch of stuff like that, like where I just say random stuff, and even though I'm talking mathematics, it actually applies to regular life. Okay, so the first one we said was not a function, and the second one we said yes. All right, let's look at it. So the domain of R are the set of inputs, which are x values, which are -1, 1, and 5. The range of R are going to be the set of outputs, which are 2, 3, and -3. But this is not a function because two order pairs have the same first component. In other words, we have repeating x's. So example A is not a function. Before we move forward, let's identify the domain of f. Just take a moment. Can you identify the domain of s? In other words, what are the set of input values? The domain of s, I don't know why I keep wanting to say f. The domain of s should be -2, 0, 2, and -1, right? The set of inputs. The range of s should be 1, 2, and -3. Notice when I listed out the domain and range, I did not repeat components, right? So the domain of s is what we said, the range is what we said, and this relation is a function because we don't have repeating x's, right? We're functional. Cool, yeah, I definitely got to update that QR code, so I probably won't do the late thing today, because again, I definitely made changes, so I'm not gonna hold you guys, I'm not gonna penalize you guys for that. I'm just trying to show my thing. All right, so I'm gonna have to cool, thank you. Born. And this one. Cool. Yeah, so I am aware. Let me disable that because that's totally distracting. Annotate. Cool beans. That should stop that. All right, I'm gonna let that ride. Yeah, I'm aware the QR code is not right, so obviously I'm not gonna penalize anyone for being late today. Not your fault. So I'll just have to update that a little bit later, probably as soon as I let you guys go. Let me see the time. We are doing pretty good on time. Okay, let's move forward. So in this example, we're asked to determine whether y is a function of x for each equation, right? Let's see. I feel like that's missing something. Part A looks like it's missing something. Let me go like this. I'll put my YouTube in the chat. When you start the homework, it takes you right there. It's Beautiful Mind Pfeiffer. Yeah, I'm not gonna do a link right now, but yeah, it's on our Blackboard page. There's a direct link. The first assignment, it takes you directly there. It's linked to it's located in several places in our thing. Okay. I feel like this is missing something. I'm going to actually look at the result here. It looks like it's missing a y. Oh, let's go like this. Yeah, 6x squared. I think that's supposed to be -3y. I was like, that didn't look right. Okay, so I found a typo. For part A, where it had 6x squared minus x equals 12, it's really supposed to be 6x squared minus 3y equals 12, right? So we'll just follow along with the typed notes. So then if we start here with the 6x squared minus 3x equals 12, so then if we solve for y using algebra, we want to isolate the y. So we want to get the y by itself. So the inverse operation of -3y, that's why they did plus 3y on both sides, right? Just like in life, you want to be balanced. What you do on one side, you do on the other. So that's what we do here, right? So if we add 3y on one side, we do it on the other side of the equal sign as well, right? And then if we want to move the 12 to the left, the inverse operation of positive 12 is -12. So that's why we subtracted 12 on both sides, right? So then now once we simplify, an expression plus its opposite adds to 0. An expression plus its opposite adds to 0, right? So essentially that's gone and this is gone, right? So then we're left with, that's where this 6x squared minus 12 equals 3y comes from. So then we ask ourselves, if we're trying to get the y by itself, we have 3 times y. So what's the inverse operation of multiplication? Division, right? So now if we want to move the 3 to the left, the inverse of multiplication is division. So if we divide both sides by 3, notice that 6 divided by 3 is 2. 12 divided by 3 is 4. 3 divided by 3 is 1. So now we were able to get y in terms of x. If you were to look at this graph, every x would correspond to exactly 1 y. We don't have a case where one x corresponds to 2 different y's, right? So we were able to get y in terms of x, right? So this is an example of something that is a function, right? We're going to explore some more ways where you can see that better, all right? I'm just going to kind of let that be for right now. Let's look at this one, though. So if we did something similar where if we tried to solve for y in terms of x, right? I kind of want to work this one since I know the original is correct. Let me work it so you can see it. I'm going to use this color, okay? So if we start with y squared minus x squared equals 4, and let's solve for y in terms of x, right? So if I mirror what we did on the previous, say I want to move the x squared to the right, the inverse of negative x squared is going to be positive x squared. So I have this y squared minus x squared. Now I'm going to add x squared to both sides of the equal sign. Okay, boom. Okay, so a number plus its opposite, so these add up to 0, so they're essentially gone. And that leaves us with, and let me line up my equal signs right here, like this, boom, okay. So this leaves us with y squared equals, I'm going to write it like this, x squared plus 4, right? So now to get rid of the square, the inverse operation of squared is going to be square root, right? And we're going to talk about this later. But whenever we introduce square root, we have to do plus or minus, right? So square root cancels squared. On the left, we get y equals. On the right, we get plus or minus, right? So that plus or minus. So now, because of that plus or minus, basically, we have one x that corresponds to 2 different y's. For instance, 1, 2, 3, 4. Okay, I was trying to think of something simple, but okay, for instance, let x be 0, right? If x were 0, then the result would be plus or minus 2, right? So you have one x that corresponds to 2 different y's, so then that's what makes this not a function. All right, hopefully that made sense. But the main thing there was when we took that square root, whenever we do square root, we have to introduce the plus or minus, and that plus or minus causes one x to correspond to 2 different y's. So then that's what makes this an example, not a function. Okay. I'm going to leave what I have written there, and I'm going to make a link. So in Blackboard, I made a folder, I think it's folder number 7. There are links in there to any PDF that you see me writing. You can actually access the PDFs there. Okay, let's kind of keep moving. Yeah, let's kind of keep moving. So we did this one, and then here, again, 2 values of y correspond to each value of x, so y is not a function of x, right? Let's just kind of keep trying some of these. I know this is a little bit much. Cool, we got another person that found it. I had to go and update that QR code. I think I'm gonna just make a fresh one and then just use that one. I thought I had updated it, but I guess I hadn't. Okay, let's keep it moving. And I mean, I don't mind keeping moving because this is being recorded. This is so you can always go back and like see what you need to see. Let's take a look at this one. So let g be the function defined by this equation. Evaluate each function value, right? So now with these examples, again, a common error that students like to do is they try to multiply. Like if we're looking at part A, students try to multiply that 3. For the sake of time, I kind of want to use the type, but I'm going to try to fit it here. Okay. I don't need this out of the way. Okay. So for part A, friends, for part A, we're asked to evaluate g of 3, right? So then that's going to be, let me see, let g be this function. So all we're basically doing is replacing each x with those things in the parentheses. Now my recommendation is whenever you do the substitutions, start by replacing the x with a blank set of parentheses, right? And so what I mean by that, instead of writing x, I'm going to write x squared like this, minus 6x plus 8, right? That's what I'm going to do. And then into the blank parentheses, I'm going to put the value, the number being evaluated. So for this one, x is going to be 3. And again, I got that 3 from right here, style. Okay. So now at this point it's algebra. All right. I'm kind of running out of space. I probably should give myself more space. 3 squared is what? 9. 6 times 3, that's going to be minus 18, and then plus 8. Negative 18 plus 8 is negative 10. 9 minus 10, ultimately that should be negative 1. Okay, hopefully that made sense. Let's try another one. So this is evaluating a function at a value. All right, let's try another one. Can we just like move you? I suppose you can go to the bottom. That might be better. Okay. Maybe at the top. Sorry, I'm just playing with some of my features here. Okay. Okay, so then part B. We'll actually evaluate g of negative 2. Okay. So again, same thing. Let's start with a blank set of parentheses. We got x squared minus 6x plus 8 equals. I'm going to go ahead and make a copy of that because I'm going to be doing that the whole while. Okay, let's copy. Okay. So now, in this case, in part B, x is going to be what? Negative 2. Negative 2, all right? So now if we evaluate, negative 2 times negative 2 is what? Positive 4. Negative 6 times negative 2 is positive 12 plus 8, right? 12 and 8 is what? 20 plus 4. That one should be 24. We're going to check these momentarily. I'm just doing them for now. Okay. All right. Let me see the time. I'm not going to stress about time. Let's keep it moving. Because of the way we're doing it, we actually have a vast amount of time. We just need to keep moving, keep hustling. Okay. So next we want to look at g of 1/2. Can I move this? That would help. That's okay. G of 1/2. Okay. Because I use that one frequently. I'm going to go ahead and just paste that same thing. Okay. So in this case, our x that we're considering is 1/2. 1/2. Now keep in mind, you can use calculators, right? You can just use calculators. Now I'm going to do this, attempt to do it by hand. I'll check the chat in just a moment. I see the notification. 1/2 times 1/2 is 1/4. Minus half of 6 is 3 plus 8. 8 minus 3 is 5. So 5 1/4. I'm going to put 21 over 4. Okay. So some things I expect that you already know coming into college algebra. I do expect you to have be familiar with factoring. You know, I don't really expect you to be like a master of factoring. That's why we have the lab component to kind of address that. But you should at least have been exposed to factoring. I do expect you to know how to, handle decimals and fractions, do basic arithmetic. So what we're going to be doing here is using that arithmetic to start to solve for like unknown parts of the equation, right? And use it to solve, using arithmetic to solve for a missing link, right? I'm just going to go with this for right now and try to finish out the rest of it. So then part D, and I'll check the chat in just a moment, g of a plus 2, let's kind of be consistent. A plus 2. And then I'm going to paste. And just for the sake of like getting it to fit, what I'm going to do let's copy this, paste. And I'm just going to shrink this down instead of trying to write and fit that. Let's copy, paste. Okay. So this is like foiling, right? So then a plus 2 times a plus 2, you have to use FOIL. Make sure the student got attendance. Cool, he found it. So yeah, I'm just giving out full attendance credit today. It's okay if you're late, because I do realize that, you know, the link probably was not updated properly. So I'm going to have to update the links later. As long as you get into the session today, you get your attendance credit. Okay, because that's definitely on my end. Okay. So a plus 2 squared, I'm not going to show the full right now. I'm just going to write the result. So it's going to be a squared plus 4a plus 4 minus 6a minus 12 plus 8. Okay. And if we take it one step further, combine like terms, a squared, 4a minus 6a is a negative 2a. Let's see, 8 plus, I think those cancel, right? Because 4 plus 8 is 12, and then 12 minus 12 is 0. So I'm gonna submit this one as my final result there. Okay, the spacing wasn't too terribly bad. I know there's one more. Part E. Okay, I'm just gonna rely, well, let me just try. Part E, we have g of x plus h. G of x plus h. I know I'm out of space. I don't know why I won't just go ahead and make some more space. Let me copy this. Copy, paste. I could shrink that down. I don't really want to. Okay. I'm just going to try to get it to fit. So the final, let me see if I can, how far, I still need a little bit more space, but let me see. So we're still going to have that same first part. Oh, sorry. And that's not a plus 2, that's going to be x plus h. X plus h, x plus h. I'm just running out of space. Let me see, we're going to have x squared plus 2xh plus h squared minus 6x minus 6h plus 8. I'm actually going to leave it like that. We have some like terms in there, but, you know, the variables, I think, are essentially different. So I'm going to go with that. And I'm going to do like this. And just try to, I'm going to leave it kind of thin. I can thicken it up. Okay, that's fine. Okay, so I was just more so concerned with space, and I really didn't want to put it on another slide. Let me check the chat. I think I saw some activity in the chat. Let's see. Yep, somebody was able to pull it up. Cool beans. Thank you for that. Because I could have done that, but I was like, yeah. Let me see the time. All right. I want to keep you for about another 10 minutes. I want to let you go at about 9:45. So let's kind of keep going. I'm probably not going to finish this right now. I have to make a decision with that. But let's keep going. Let me see. So the first one, we got -1, 24, 21 over 4. This all looks good. You see a typed version of what we did. And I think everything else looks okay. Yep. It looks fine. Okay. All right. So let's go through this agreement on the domain. If the domain of a function that is defined by an equation is not explicitly specified, then we take the domain of the function to be the largest set of real numbers that result in real numbers as output, right? So that's just like a general statement. You just wanted to, because like sometimes what happens is like you need to like you need to specify the domain. If the domain isn't specified, then just take the largest domain that you can. Let's kind of take a look at this. So we're asked to find the domain of each function. Okay. Do I need more space? I don't think so. So for instance, if we're looking at part A is what's called a rational function. Basically, it's like a fraction, right? So for part A, in general, the domain of rational functions is going to be all reals except any x that makes the denominator 0, right? So for part A, what I mean by that, for part A, the domain is going to be all reals except any x that makes the denominator 0. So then the next logical question should be, what x makes the denominator 0? So if we want to find the x that makes the denominator 0, all we do is set the denominator equal to 0 and solve. And let me put that in purple so you know that's just like my suggestion. All right, we're going to set the denominator equal to 0 and solve. So if we say 1 minus x squared and we set it equal to 0 and solve, we can add x squared on both sides. We get 1 equals x squared. You take the square root, x equals plus or minus 1. Remember, whenever we take the square root, we have to introduce plus or minus. So the claim is that we need to throw out plus or minus 1. So the domain is going to be everything except, I'm just going to show it like this. Everything except, I'm going to put a slash with the equal symbol. So the domain is basically everything except plus or minus 1. I'm just going to go with this for now for the sake of space. I would like to keep all this on the same slide, but if I need to create space, I will. Okay. Let's look at part B. So part A, again, that's called a rational function. In general, for a rational function, the domain is everything except any x that makes the denominator 0. For part B, that's called a radical equation, right? Where we're basically dealing with the square root. Whenever we're taking the square root or any even root, like 4th root or 6th root or anything like that, 8th root, any even root, for instance, we cannot take the square root of what kind of numbers, right? Like, for instance, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is what, 2, square root of 9 is 3, so on and so on. So what kind of numbers can we not take the square root of? We cannot take the square root of, hopefully you're thinking, negative numbers. I don't know if you watched Dora the Explorer. Say it with me. Can you say negative numbers? Say negative numbers. So I never really watched Dora the Explorer, but I did watch Dora the movie, the live action movie. That movie had me, almost in tears. It was way funnier than I thought it was going to be. Not that it's funny. It was just funnier than I thought it was going to be. So I definitely had a Dora the Explorer moment there. It was a fun the live action movie was fun. Anyway, to get back on task, I'm watching the clock. I see we have a solid 5 minutes. Again, we cannot take the square root of negative numbers, all right? So for the domain for B, we need to throw out any x that's negative, right? So for B, the domain is going to be, x has to be greater than or equal to 0. And that's just going to be my abbreviated notation. We'll look at proper notation momentarily. I'm just trying to get you to see some concepts. So again, the first type was called a rational expression, where it's basically a fraction, and we have to throw out any x that makes the denominator 0. For part B, that's called a radical equation, and we cannot take the square root, we cannot take an even root of negative numbers. So that means the radicand, which is the inside part, has to be greater than or equal to 0. It's a little bit of a mouthful, but you'll start to see it. Again, since we cannot, x can't be negative, it needs to be non-negative. In other words, greater than or equal to 0. So part C actually combines both of those concepts together. We have two restrictions. Not only can the denominator not be equal to 0, but we can also not take the square root of negative numbers, right? So if we focus on the radicand first, the first thing is that x minus 1 has to be greater than or equal to 0. But again, because we can't have 0 in the denominator, the only restriction, we have to impose an additional restriction. So originally, the x minus 1 would be greater than or equal to 0. But because this expression is in the denominator and it cannot be equal to 0, we got to get rid of the equal sign. So then the restriction is that the x minus 1 has to be strictly greater than 0, right? Strictly greater than 0. So now if we solve for x, we're going to get x has to be strictly greater than 1. And that's going to be the domain there, okay? So part C combined both the concepts together. Can't have a 0 in the bottom of a fraction, and we can't take the square root of a negative, and so you saw how it evolved. Let me make sure the student got attendance credit, because I do realize that there was something there. He looks good. I'm going to let him in. And let me see the time. Let me go ahead and do part D, and then I'll probably let you go. Okay, so we kind of discussed this. Again, we can't take the square root of a negative. So for part D, then the radicand, which is this x squared plus 2x minus 3, that needs to be greater than or equal to 0. Okay. So for this one, this one's a little bit involved. We have to factor this. Let me go ahead and factor this trinomial. We got x and x plus and minus positive 3 and a negative 1. Notice that 3 times negative 1 is negative 3, right? 3 plus negative 1 is a positive 2, right? Let's see. So I'm going to use a quick graph to find the domain. So from here we get that x is negative 3 and 1. So if I plot on a number line, if I plot on our number line, come on. I see the time. I'm about to let you guys go. So we get negative 3 and we get a positive 1. All right, these are going to be our zeros. So we want to know, when is this expression positive or above the x-axis? So for instance, if we choose something to the left of negative 3, say we plug in negative 4. I see some activity. If we plug in negative 4, this is going to be negative, this is going to be negative. Double negative is positive, right? So if we plug in negative 4, everything to the left of negative 3 should be positive or above the x-axis. And again, this is like the x-axis here. Let's choose a number between negative 3 and 1, like 0. If we plug in 0, this is positive, this is negative. A positive times a negative is negative. So everything between those are going to be negative or below the x-axis. Choose something to the right of 1, namely 2. If we plug in 2, this is positive. Here, let's see, this is positive. This is positive. Positive times positive is positive. So everything to the right of 1 is above the x-axis. So when is this positive? So the domain there is going to be, the far left is negative infinity up until negative 3, and then from 1 to infinity. Whenever we're talking infinity, the grouping symbol for infinity is always parentheses. Because we can be equal to 0, the 3 gets a bracket and the 1 gets a bracket. The square bracket means we can be equal to that number, right? I know that's a little bit intense. Let me kind of close this out so I can send you guys on your way. You definitely, again, you want to link up with the tutors. I think I loaded a handout on to the tutoring information. Give me just a moment. Just want to clean this up some. Undo. Let's try that again. Can avoid that stuff right there. Cool. So this is the result we got here. I'm just trying to make it a little bit more aesthetically pleasing. Okay. Okay, I'm about to let you go. Let me just kind of compare this to theirs. We got, so for part A, oh, I forgot the interval notation. So again, we said that everything except plus or minus 1. So then this interval notation that you see at the bottom is everything except 1. Again, parentheses means we don't include that number. We never reach infinity, so that's why infinity gets parentheses. We don't include the plus or minus 1, so that's why they get parentheses here. So this notation that you see at the bottom means everything except plus or minus 1, right? This one was the same thing that we got. So x was greater than or equal to 0. So we're basically talking about 0 to infinity. I think we got the same thing here. We went through the explanation there. X was strictly larger than 1, so 1 to infinity. And we walked through this one as well. We're about halfway through the slide. So what I'm going to do, let me check the chat really quickly, see if there are some questions. There aren't any questions. I re-engage my audio. If you feel like you need to unmute yourself, feel free to do so now. If there aren't any burning questions, I'm actually going to let you guys go. And probably what I'm going to do, I'm probably just going to go ahead and finish out this presentation, so I can have one clean set for this one clean video for this topic. Let me see. I think he's in another class. Okay, guys, if you don't have any questions, I'm gonna let you go. You're welcome to stay. I'm gonna keep streaming if you want to stay and like see the rest of this presentation now. But if you gotta go, I totally get it. Go ahead. Hmm. I would I would talk to Doc. I put some contact information in the handout section on Blackboard. I would contact Dr. Lamar for that because she's running the lab. So whatever she says, that's what you need to do. Because she's the one that's going to be like the point person for the lab, and I'm just gonna whatever she says, I'm gonna take it and give you a grade accordingly. Yep. Okay, guys. So again, you're welcome to stay. You're welcome to leave. I'm going to continue this section and go ahead and finish it out. Yeah. Let me. But I'm gonna mute my audio. So if you need to contact me, just type it into the chat. Okay. So that was that one. So let's take a look at this one. We have f of x equals x squared, where the domain uh, is restricted from 3 to 5. Is a closed interval from 3 to 5. Is 10 in the range of f, right? So if we consider the range, which is the output, which is 10, okay. I think we can do that here. Okay, so with this one, I'm going to just kind of tell you like, with the domain being restricted from 3 to 5, we call that monotone increasing, which means that when we look at the graph and we restricted the domain from 3 to 5, the graph is always going up, right? So you don't have to worry about it like going down or anything of that nature. So what we're going to do here is test the endpoints and then see how the cards fall. Let me update. Let me update attendance. So I know some brothers didn't find it. I'll just be aware that hey, they might need to be excused because they just need to reach out. And because if they say they couldn't find it, then I'll give them credit. Okay, let me close that out for right now. So then for part A, is 10 in the range, right? So for part A, let's first let's do f of 3. If we do f of 3, that's going to be 3 squared, which is 9, right? And then let's also consider f of 5. So that's going to be 5 squared is 25. So all the outputs in this case are going to be between 9 and 25. So it's 10 in the range, so then part A would be a yes. Okay, that would be a yes. Part B is 4 in the range. Part B, you can just look at it because we just did it. 4 is outside the range because the range in this case goes from 9 to 25. Is 4 in the range? We're going to say no. Okay. And then part C, find the range. Did we find that range properly? Okay. So for part C, I'm just going to say basically the range. So I'm going to say y equals, it goes from what, 9 to, I think it's 9, it should be 9 to 25. Hopefully I did that right. We're going to see like right now. Hopefully my logic there was sound. Sometimes I do make mistakes. Okay, we're going to let that be. Let's kind of look at it. So for part A, we got yes. Yeah, they basically, okay, so they did this different. I probably should have did it their way. If we put 10, if we set the function equal to 10 and solve, right? We set the function equal to 10 and solve. We get plus or minus the square root of 10. So because the square root of 10 is between, but positive root 10 is between 3 and 5, the number is in the interval. So f of x equals 10 has at least one solution in the domain. Therefore, 10 is in the range, right? So because there's at least one in the interval, then we say that this is in the range. But if we try the next one and set it equal, if we set it equal to 4, we get plus or minus 2. Notice that plus or minus 2 are not in the domain, all right? So then 4 is not in the range. And then to find the range, so they consider f of x, but then, let me see, did they solve? So they solved for y, or they solved for x. So x, okay, so if we start with like y equals x squared right here, if we start with y equals x squared and we solve for x, so then x is going to be equal to the plus or minus square root of y, but I think we're just going to take the positive. So then f of x equals f of the root x, which is equal to f of root y, which is root y squared, which is y. Now, the way I presented it, I've seen it done that way. That's, we'll kind of keep working with that stuff and like address these as they show up. I'm going to let it be for right now. Okay. So then we have this notion or this idea called the vertical line test. It says that if no vertical line intersects the graph of relation at more than one point, then the graph is a function. So this example that we have shown is an example of something where if we draw a vertical line, it touches the graph more than once. So then we say that this is not a function. This is an example of a graph that fails the vertical line test. So then we say this is not a function. Okay. So determine whether the graphs in the figure are graphs of functions. In other words, if we can draw a vertical line, and it touches the graph more than once, let me do like this one. Okay, that looks better. So again, if we can draw a vertical line and it touches the graph more than once, then it's not a function, right? So we have a vertical line. Notice right here, it touches the graph more than once, so this is not a function. Okay. Not a function does not pass the vertical line test. Okay. Same thing here, right? If we draw a vertical line, we can find a place where the vertical line crosses more than once. Right here, and right here. So this is not a function. Okay, not a function. Notice here, no matter where we place the vertical line, it touches the graph once, right? We can't find somewhere where we can draw a vertical line and it touches it more than once. So this is, yes, a function. Okay. Same thing here. Yes, a function. Again, no matter where we place the vertical line, it only touches the graph once. Okay. Okay. So let f of x be this. Okay, so the first question, part A. Is the point 1, -3 on the graph, right? So when x is 1, is the corresponding y -3. So let's consider f of 1. That's going to be 1 squared minus 2 times 1 minus 3. That's going to be 1 minus 2 minus 3. What is that? -4. Right? So is that point on the graph? That would be a no. Style. Okay. Find all values of x such that the output is 5. Okay, so then for part B, we're basically setting this equal to 5. So we have x squared minus 2x minus 3. We want to set it equal to 5 and solve. So if we set this equal to 0, we'll get x squared minus 2x minus 8 equals 0. Okay, let's see, can we factor this? All right. So we got x and x plus and minus. Is it 4 and -4 and 2? Let's try 4 and 2. -4 times 2 is -8. -4 plus 2 is -2, right? So then from there we get that x equals -2, and +4. Those are the x values that when plugged into the original should give us an output of 5. Okay, well, I'm going to shrink this down and just compartmentalize this really quickly. I don't know if compartmentalize is the right word, but hang on. I'm just trying to get it to fit here. And actually, I'm going to drop this down a line as well, just for the sake of space. Okay, that's going to have to work for now. Okay. Part C, find all y-intercepts. Okay. So again, when we start doing x and y-intercepts, whenever you have a choice, I would recommend finding a y-intercept first. More often than not, finding a y-intercept is often easier than finding an x-intercept. There are times when the x-intercept is just like, it's a lot of work. Okay, let's go to C. So then C, the y-intercept, so we set x to 0. So we want to consider f of 0. It's going to be 0 squared minus 2 times 0 minus 3. And that's just going to be -3. So the y-intercept is going to be -3. I'm going to write it as 0, -3. Or it might just want just -3. Let me do like this style, like that. And let me shrink this down. Okay. And then part D. Find the x-intercept. So to find the x-intercepts, we set y equal to 0. So we want to take this f of x, which is going to be x squared minus 2x minus 3. We want to set that equal to 0 and solve. Can we factor? Let's see, maybe we can factor this. Double parentheses, x plus minus 3 and 1, -3, +1. Notice -3 times 1 is -3. -3 plus 1 is -2. Okay, so then from there, we get what? X equals -1 and 3. I think we're okay there. And then, we would check by plugging back into the original style. Okay. Oh, well, we want x-intercepts. I mean, we could probably leave it like that. I'm just gonna, let me undo. I'm gonna write them as ordered pairs. It's the same. It's just the same thing. So the x-intercepts -1, 0 and 3, 0. Right, that's where they cross the x-axis at those points. And they might want x equals y equals. It's just, we'll straighten all that out. Okay. Okay, well, we got it to fit. We got no, then we got -2, 4. We got 0, -3, and then, okay. We got no. Okay, so we got those x values. Oh, yeah. -2, 4. So we got the same thing. That's fine. Y-intercept is -3. I think that's what we got. And then -1, 3. Cool. Okay, that's fine. We're almost there. Didn't take us as long as I thought. Many drugs used to lower high blood cholesterol levels are called statins, and are very popular and widely prescribed. Bioavailability is the amount of a drug you have ingested that makes it into your bloodstream. I think it's called a statin. A statin with a bioavailability of 30% has been prescribed for Boris. Boris is to take 20 milligrams of the statin every day. During the same time, 1/2 the statin is filtered out of the body. Find the maximum concentration of the statin in the bloodstream on each of the first 10 days using the drug and graph the results. Let me see. 30% has been prescribed. Boris is to take 20 milligrams of the statin every day. During the same time, 1/2 the statin is filtered out of the body. That's the amount in the blood minus half of that. Let's see. So since the statin has a 30% bioavailability and Boris takes 20 milligrams a day, the maximum concentration in the bloodstream is 30% of the 20, which is 6 milligrams. Because half of the statin is filtered out of the body each day, the daily maximum concentration is the previous day's maximum concentration, or half the previous day's maximum concentration plus 6, right? Okay. So on day 1, the previous concentration was 0, and so he should have 6 milligrams of the statin in his bloodstream. And day 2, okay, and that makes sense. That's the part I was getting a little stuck on, right? So we see how to build the formula, and then from there you can kind of create a table, right? And you should be able to generate these points, and then you can plot them. And you get something like this. So then it says that the maximum concentration approaches 12 milligrams. Okay. All right, we're going to kind of let that be for now. That didn't take much longer. I thought it was going to take much longer than that. It didn't take too much longer to kind of finish out this section. No major announcements I could think of, so we're just going to actually end the session here. Okay. And from one beautiful mind to another, enjoy the rest of your day. Peace.